All right, let's get started. Good morning, everyone. Today we will be continuing what we have started yesterday on graphical analysis of one-dimensional motion. This will be very brief, and then you guys will start the first lab, okay? So yesterday we wrote down the one-dimensional kinematic equations of motion. So I will just write them down again because you will be using them. So we have the first equation, the velocity at any moment of time is equal to the initial velocity plus acceleration times time. Second equation, position at any moment of time is equal to initial position plus initial velocity times time plus half acceleration times time squared. And then the third equation, which we didn't prove, and we said it's proven by eliminating the time from one equation and substituting it into the other equation, so it doesn't have new information content, but it's important nevertheless. So v squared equal v naught squared plus 2a delta x, where here delta x is just x at any moment of time minus the initial x. Okay, so these are very important. I will have them in a separate box here. So today we don't want to look at the equations as equations. We want to graph them and see how we can interpret the results from graphs. So the notation x of t and v of t already reminds us of function notation. Like, remember when you have a function f of x, for example, we say that f as a function of x, you can imagine schematically the function as follows. It takes an input, x, this is the input, and then it spits out a result or an output, f, and this is the function f of x. So in our case, if we look at the position, for example, we give the function the time, let's say 3 o'clock, and then it spits out the position of the object at 3 o'clock, where the object is. We can graph that just as we graph functions. So let's take some examples. So first example will be no motion at all. The object is just sitting still, no motion. Okay. So let's say I'm sitting here. My position is some x0, initial position. So there is no acceleration, there is no velocity. And this is, let me be clear, velocity and acceleration at any moment in time is equal to 0. So now acceleration is equal to 0. After 2 seconds, still 0. I'm still sitting here. And the position, my position at any moment of time is equal to the initial position that I already had. And this follows from the equations above. If you set a equal to 0 and v equal to 0 in this equation, you will get x as a function of time is equal to x naught. So it's just a special case from the above equations. Now, if we want to graph that, let's start with acceleration as a function of time. We always have the independent variable being on the horizontal axis and the dependent variable on the vertical axis. So the horizontal axis varies as we want. And then we see, with respect to that independent variable, how the dependent variable behaves. So 1, 2, 3 seconds. time in seconds and acceleration in meter per second squared. My acceleration is 0 at any moment, so it's just started at 0. After 1 second, it's 0. After 2 seconds, 0. So it's just a line here at 0 value. Velocity is exactly the same way. It will also be a line at 0 position or at 0 value. Position, however, will not be at 0 unless I stated my initial position to be 0. But the point is, it will be the same at any moment of time. So it's a straight line like this. It doesn't change. So at 1 second, 2 second, 3 second, etc., it's still at the same value x naught. So this is the case of no motion at all. Okay. Let's make it a little more interesting by allowing motion but without acceleration. So let's say we're moving with constant velocity. Okay. So motion with constant velocity, which means acceleration at any moment of time is equal to 0. Let's substitute a equal to 0 in the original kinematic equations here. So if we did that, the second term in this equation here will vanish, and the third term in the position equation will vanish. I just want to show you it's all coming from the original equations. They're not new equations. So we will have velocity as a function of time is equal to the initial velocity. Nothing happens to it. It stays at the same value. And position at any moment of time is equal to initial position plus V naught times T. Okay. And again, acceleration is 0 by definition of constant velocity. So if we wanted to graph that as we did above, let's start with acceleration as a function of time. It's still not interesting. It's 0. So it's here, just a line. But velocity will not be 0 anymore. Assuming velocity is positive, if our initial velocity is to the right, moving to the right, then the graph is like this. So at the first second, second second, third second, velocity has the same value, V naught. It didn't change. Okay. We can have a negative velocity if we're moving to the left. In that case, our graph will just be something like this. If we had it to be negative velocity, okay? But let's stick with positive velocity just not to confuse the graph. But you should know you can have negative velocity as well. Position is interesting here because this is the equation of position, right? So let's take it point by point. So at t equal to 0, we're sitting at x naught here. Okay. At t equal to 1 second, now we are sitting at x naught plus v naught, right? So this is a new value here. Then at t equal 2, we are sitting at x naught plus 2 v naught, right? So this is another point. If we connect the dots, we get a straight line. Okay. So, and this should not be surprising. If you remember from algebra, the equation for a straight line is y equal mx plus b. If you remember this equation, where m is the slope of the line and b is the y-intercept. This equation, when graphed, looks something like this. Y versus x, it's something like this, where this is the b-intercept, the y-intercept, sorry, so this distance is b, and the slope of the line is equal to m. This is just an equation, or the equation of straight line. If you compare that to the position equation above, we have x instead of y and t instead of x. So, but we have the same form still, v naught t plus x naught, right? So the y-intercept here is x naught, right? Or the vertical intercept is x naught. So this is the initial position we started at. And the slope in this case is the velocity. And this is what we mean when we say the velocity is the slope of a position versus time graph. So let me write that down. So slope is equal to, rise over run. In this graph, rise is this here, this part, which is V naught, right? And the run is 1 second. So when you divide V naught by 1, it's just V naught. Or in general, it's delta X over delta T, right? You move a little bit in the horizontal axis, which is time, and you get a result of change in position, which is delta X. You divide rise over run, you get delta X over delta T. This is exactly how we defined average velocity. So we get the same expression. So this is average velocity. Okay. And if we want the instantaneous velocity, we just make this delta T smaller and smaller. And this corresponds to looking at the tangent of the curve. Okay. The slope of the tangent. Okay. So this is average velocity. Okay, let's take another example for this time, not constant velocity, but constant acceleration. Constant acceleration. Now the equations don't change. The kinematic equations, they're the same. Constant acceleration mean acceleration at any moment of time is just a, it's the constant. V as a function of time is equal to initial velocity plus a times t. I know I'm repeating these equations a lot, but I want them to stick at your head. V naught t plus half a t squared. These are the equations from which we will draw a graph. So let's draw acceleration versus time again, as usual. Assuming acceleration is positive, assuming the object is accelerating to the right, the change in velocity is to the right, not the motion itself. So assume this value is a, then this is just a straight line, horizontal straight line, because the acceleration doesn't change at any point. Velocity versus time. At t equal to 0, it's v naught. This point is v naught. At t equal to 1, it is V naught plus A. I don't know what's happening to my pen here. And if you do the same thing over and over, you connect the dots and you get a straight line. Finally, position versus time. From the third kinematic equation, at t equal to 0, we just get initial position, x naught. At t equal to 1, let me make it a little more wide. At t equal to 1, we get x naught plus v naught plus a over 2, right? So it's just some value. When we get numbers, that will be easier. And at t equal to 2, we get another value. Just don't want to write it down because it's too long. But anyway, the graph will look something like this, which is a curved graph. It's a parabola. Okay. And this makes sense because if we think about the slope of position versus time graph as the velocity, at constant acceleration, velocity is increasing. If the object is accelerating, the velocity keeps getting larger and larger. So if you look at the slope here, this was the slope. It was close to horizontal. Then it tilted a little bit, so the slope is larger. And then it gets even more larger, so the slope is increasing. So this graph makes sense. So here, slope of position versus time graph is equal to velocity, delta x over delta t. This is velocity. At a point, it's instantaneous velocity. And the slope of velocity versus time graph, delta v over delta t, this is now acceleration, right? For this graph. So from xt graph, we get velocity. From vt graph, we get acceleration, okay? From at graph, I don't know what we get, but you can calculate the slope as well, but I don't know if that's physically relevant. Okay. It's not necessary that you will always have motion with constant acceleration, constant velocity, or no motion at all. You can have motion with varying acceleration. For example, if you're driving your car, you don't always accelerate with the same rate. Otherwise, you will have very big velocity at the end. But you brake and then you accelerate and then you take turns. So it's variant, okay? But in general, it's always the case that when you take the slope of velocity versus time graph at a point, you get the acceleration, the instantaneous acceleration, and you get the instantaneous velocity when you take the slope at a point of xt graph, okay? So in a sense, graphs are more generalizable than equations, okay? So if we are given an equation, we can extract from it the quantities we want. So let's say we are given, I didn't tell you what acceleration is, I didn't tell you what velocity is, I didn't say anything, I just told you, okay, let's assume we have an object whose position satisfies this equation. I just gave you this equation without saying anything. This is the position of the object at any moment of time. Okay, this is an example. This is example. Okay, and I asked you, what is the average velocity between t equals 0 and t equal 2 seconds. Because to calculate the average velocity, you have to specify a time interval. You cannot just say average and then don't say the interval, because the average velocity is variant. So in that case, the first step to do is to draw a graph. First step, draw a graph. And I always find it helpful to write down a table. Even if this is elementary, I still find it useful. T versus X. So if T is 0, I look at X and substitute 0. So 4 times 0 squared plus 0, I get 0. Then at 1, you get 1 plus 4 times 1, so that's 5. Then at 2, you do the same thing again, you get 17, and so on. So you choose a couple of points just to be representative of the graph you want to draw. Okay, and then plot the points. So at t equal to 0, this is X. At t equal to 1, let's say this is 5, this is 10, this is 15. I'll need more space. And this is 20, so around here will be 17. So at 1, I get 5 for X. And at 2, we get 17. So this is the graph you get when you connect the dots. Okay. Now, if you want to calculate the average velocity between points in time from 0 to 2, you get the slope, the rise over run. So here, the rise is this part, which is 17, like from 0 to 17, and your run is 2, right? So the average velocity in this case is 17 minus 0 over 2 minus 0. So this is 17 over 2, which is just 8.5 meter per second. 18. Why 18?
Because if it's 2 squared, that would be 4 times 4.
Right, that's correct. Yeah, I'm sorry.
That's fine.
Yeah, my bad. That's why I need to have a calculator with me, because my brain is not working properly. Here. Okay, so this is 9 meter per second. Thank you. Okay, and you can do the same thing and collect some points for average velocity to draw the velocity versus time graph, and do the same for acceleration. This is probably fine, but you can also be given the graph without being given an equation. Okay, so this is the last time I will give you today, and then you'll start the lab. So assume we're given an arbitrarily shaped graph of position, for example. I will try to make it not so arbitrary. So assume you were given this graph. or position. Okay. And you are asked to get the velocity versus time graph and acceleration versus time graph, because this is what you will see in the lab. So we said velocity is the slope of position. So we will look at the slope and how it varies on the xt graph. Okay. So at the beginning, the slope was 0 because it's just a tangent line. So that corresponds to 0 velocity, t equal to 0. At, let's say here, let's call this 1 second, for example. Just make sure to have it equally spaced. Because we're not given equations, so we have to be a little bit more careful with that, with the spacing. So here, this is the slope. This is the tangent line. So it increased a little bit. So we know that the velocity has increased. So let's say at 1 second, the velocity became here, for example. We don't know what the values are. We're just doing it schematically. And then here, the slope was much higher. So that means the velocity is increasing linearly, right? It's steadily increasing. So we get another data point and connect them. So it looks like we're getting something similar to a straight line. And then we see at this point at the top, it becomes to, it starts to slow down a little bit, right? Because the slope is now getting, let me put the slope up. Because the slope here is starting to go down again, right? So the velocity is starting to get lower. So let's say here, and then at the top, at the very top, it becomes horizontal again, which means 0 velocity. So velocity must have hit the 0 point on this axis. So if we connect the dots here, this will be something like this. Okay. Then the slope becomes negative at this point. So the graph keeps going to the negative direction until it stops here at this point is where it stops. And then the position is the same. It doesn't change anymore. So that means the velocity must be 0 after this point. So this will be the corresponding velocity versus time graph. We can go on and do the same for acceleration from the velocity versus time graph, but this will probably be easier because here we have a straight line. So the slope of a straight line is constant. So we have constant acceleration, positive in the beginning here up to this point here. Then we have negative slope, so that must mean the acceleration changed direction. And then we have 0 velocity, which means acceleration is 0. So that will be the corresponding velocity, acceleration versus time graph. This is probably the hardest thing you will see in kinematics. It requires a little bit of practice, but you will get better on it over time. That's it for the lecture part. I will give you guys the activity. It's a little bit long, so if we didn't get to finish it today, we will continue with it tomorrow.